I am David Hauer. I must admit I have some big problems with archaeological wood. Or at least we have some challenges, some special challenges with our large, complex wooden objects in our collection. This is about a museum that you see here in the picture, the cross-shaped building. It's built about 100 years ago in some steps. And now we are building the circular addition to this museum that you see in this drawing. And in this process, we have some large objects. The three best preserved Viking ships in the world are in here, and some wooden sleighs that are incredibly fragile. So I was thinking of letting you know this collection a tiny bit better. These are the three ships, the Tune, Oseberg and Gokstad ship. And the years that you see here, that's the construction year and the excavation year. And these ships have been graves from terrestrial finds. So these aren't maritime finds. These are excavated from the soil. They've been used as grave chambers for people in the Viking Age. Some of the other objects we have here, this you will never be able to see again because now we close the museum, and this is the part of the museum showing the other artifacts that were in the ships. Very rich finds, everything from kitchen utensils, animals, sleighs, wagons, textiles and beds, loads of different things, making these finds extremely rich and valuable as Viking Age finds. I think we'll just go further. As you saw in the picture from the excavation date, these were excavated early 1900s and late 1800s, meaning that the conservation treatment these objects went through obviously are based upon the methods of conservation they had at the time. And this divides our collection mainly, roughly, into two groups. One that is alum conserved, meaning they have put salts, dense, very high concentrations of salt solutions. At 90 degrees, put the wood inside. Salt is pulling into the wood. Water is evaporating. Salt is crystallizing and supporting the wooden structure. The other group of objects are just, and luckily the ships are in this group, are just air dried. They control the air drying by putting on creosote to dampen the effects of microbiological deterioration, and the linseed oil to slow down the water evaporation. So this was the method they used on the ships. A downside with the alum treatment is that the wood gets extremely acid. So we have a pH of 1 to 2 in this wood, causing it to further deteriorate. But this was, of course, not the knowledge that they had at the time. But and another very bad side effect of this treatment is that the wood gets incredibly heavy. So the density of this wood, not the wood, but the object, is actually greater than fresh wood. So they become heavy, very, very fragile. And as you can see on this picture from the X-ray here, these are built up from fragments, and they have used steel pins. So on the X-rays, you can see that the acidity of the wood has actually now corroded the steel pins away. So this makes these objects incredibly fragile. What I'm going to talk about today is overall structure. So it's just for you to get a clear picture of what we mean by this. It means the whole structure. And we have conducted lots of investigation on the material level, of course, with chemistry and wood chemistry and degradation, and also mechanical testing on components. And with components, we mean all the pieces made out of one single piece of wood. So a strake here, you have this coupling here. So this is a component. A knee here is a component. But so when I talk about the overall structure, is the whole structure. So this is more details on the Viking ship. From a wooden perspective, the boards, the sideboards, creating the hull in yellow, they are radial boards taken out radially. Then you have this quite a thick board here above the waterline, along the waterline. That is sort of a transition to the upper hull that is tangential wood. And this was carefully thought out. I mean, this was a very part of the design at the Viking Age, how this should actually be done. It's very consequent, it's very well thought out, and thanks to this radial section, the radial expansion is about half the tangential for when you cycle climate into this. I mean, the climate changes in the museum. Unfortunately, also, this keel is bolted onto what we call the keel beam of recent wood. So the brown beam here is recent pine, I mean from 1911 about. So any effect on this beam is transformed into the keel and giving some effects also. When we are to, this is also this is the Oseberg ship, and all the lines, they are cracks, and all the colored areas are recent wood. The rest is original wood from 1820. Adding to the complexity is also the how they are reconstructed, these ships, because they are, except for the tuner ships, both the Gokstad and the Oseberg ships, they are torn down, reshaped and put together again into the ships we have today. And here you see lots of nails and screws and metal joints that they've used for the reconstruction. After 100 years on display, the ships are showing creep deformations. Creep hasn't been explained here, but it's just sort of deformation under load. So it's typically a structural problem for large structures and not wooden objects, smaller wooden objects. And for the sleighs, they have been on exhibition in this museum since 1957, and we have lots of these, damage. This is from 1980, cracks appearing in exhibition. Nå står vi ved det aller skjøreste gjenstanden vi har på Historisk museum. Det bransjsleden. Sorry. I didn't know what this was a film. And I'm talking Norwegian here. And luckily there are some subtitles here. This was issued last week, I think, from the museum. And I want to just ask you to note then you get a notion of what alumwood is like, because you have a few seconds in here that you see how fragile this wood actually is. At hvis vi ikke håndterer dem på rett måte, så kan de rett og slett pulveriseres. De helt unike I verden, og de dateres fra tidlig 800-tall, og de representerer noe av det ypperste av trehåndverk fra vikingtiden. Da disse sledene ble funnet, så var de knust. De ble rekonstruert av opp mot 1000 fragmenter hver enkelt slede, og sammensatt til de sledene vi ser I dag. Konservering med alunsalter var den beste metoden man hadde for bevaring av arkeologisk tre på begynnelsen av 1900-tallet. Hadde ikke det blitt gjort, så hadde vi ikke hatt sledene I dag. Likevel førte metoden til at treverket ble ytterligere nedbrutt. Det ser ut som tre, men det skal ingenting pulveriseres. Det at sledene så skjøre gjorde at flytteprosessen ble svært komplisert. Siden sleden ikke tåler å flyttes ut av vikingskipshuset, så har vi spesialbygget et rom her, hvor sledene sikret gjennom byggeperioden. Sledene nå trygt plassert på en plattform som veier 16 tonn, som I sin tur vibrasjonsisolert med luftfjærer. På denne måten blir de beskyttet mens vi bygger det nye museet, og vi overvåker sledene nøye I prosessen. So this is part of our project that is going on now. Moving on to the climate in the museum, we don't have any climate control in our old Viking ship museum, the cross-shaped building, except for some slight heating in the winter. We try to keep the temperature as low as possible, meaning around 13 to 15 Celsius in the wintertime to maintain a higher relative humidity. The summer of 2018 was in Northern Europe very dry and hot, so then we got sort of more of a winter time when it comes to relative humidity, and otherwise you see sort of the typical range of climate in the museum. When I started on preparing for the building process and moving these ships, it was really sort of, what are we going to, we have to figure out what are the main risks in this big process for us. So structural stability is very, very important. It is the main risk for further deterioration, both for the ships and the sleighs. And the main causes of structural change, they are time-dependent deformations that we've been hearing about earlier today, dimensional changes in the wood due to seasonal climate fluctuations, as I showed you through the chart of the yearly fluctuations, and stress concentration around the supports, leading to tensions and fractures around in the load-bearing areas. And vibrations, this is caused both by visitors and through the building process. We have all the machinery that is going to be on site, and we also have the process of moving that is inducing vibrations. Then a big challenge when it comes to structural stability is to move the objects, of course. And so load transmission from where they are standing, lifting them, transporting, means that there is a shift of load distribution in the object. So we try to make some sort of sense of our objects. We do scanning and we do shell elements. We've tried to figure out our interior, and we look at details throughout the structures through section cuts, and we make FEM models of the objects. The problem with numerical modeling here is that the input data is very difficult to get into these complex models. So that goes also for the slice. So we have, we'll just skip that one. We have established three methods on the level, I mean the overarching level, structural level of our objects, and by introducing 3D monitoring of geometry, load distribution monitoring, and dynamic behavior. So this is what I'm going to take you through now. We use photogrammetry with fixed targets. And the reason we did this is that it is, we need the measurements to be accurate, and the repeatability has to be very good in order to see a deformational change, and it has to have a short acquisition time frame in order to avoid dimensional change due to climate changes during acquisition. This is just a setup. Red dots are reference points, and green dots are deforming related to the red dots. This makes a sort of basic feature is that you get a slight movement at high RH. The hull is expanding and contracting at low RH. That is not the main problem, because the dominant motion is in the length direction. Because this, due to the structure of a Viking ship, you get a very big movement in the length direction by just increasing the width here slightly. And this is at low RH, then it pulls together. That was the deformation monitoring. Then you have load distribution monitoring. We have suspended all our load-bearing points. We have lifted all the load-bearing points and put them onto load cells, so we can monitor the load distribution in the object. This leaves us charts like these, where the median values are noted here in kilos, kilograms at this time, and the change through the climate range we have in the museum, plus minus. And all the red dots, they are supports and along the hull, and the yellow are the keel. Meaning we get these charts like these. Having this, we have a tool to see how the change for each support is changing in load over the year, and what the deformation rate from the deformation plots are around the supports. So we can see the mechanosorptive creep occurring at each support and as a whole structure. Going more into a sort of detailed plot, we get these. This is how it moves during the cycle of a year. It expands contracts and goes back, and we follow all the load distribution along the way. Yeah, that turned around. I don't have any more time, do I? Yeah, I would. 30 seconds. Oh, I need to say something about the dynamic analysis. We try. This was totally distorted, this on the left. It turned when I started it. We put energy into the ship, and we look at the response by operating deflection shape. We see through different frequencies what are the most, what causes the most risk to the structures, and then we look at the resonance frequencies, and then we find these charts with these red fields here are resonance frequencies at the object, and then when we design I think this is the same for the sleds. You get these mode shapes, and that is how our objects are moving at different frequencies. I've also put in some references here for those who might want to look into this more in depth. I'll then use the time I don't have to just tell you a bit about the outcome, and that is to get tailored solutions for these objects. We get, from these methods, we can see what are the effects of deformation due to climate response, seasonal climate fluctuations, what are due to mechanosorptive creep, and what are due to vibrations. So if the main problem is mechanosorptive creep, you should not focus onto climate control. Then you should go onto your support systems and establish a better support system. And if you have the problem with deformation during climate cycles, you should focus on your climate control. These are just charts also that you, from strain charts that we get from these plots of deformation monitoring during the yearly cycle. These are plots for deformation at each support. So the red are supports load on a support through the year, and the green ones are the deformation around the same point. Yeah. Would be nice to tell you something about this, but I don't think, I will do that. I'll use some of your question time. Because the dynamic motion that I showed you of from ODS, that gives us some idea of how much of the mass of an object that is engaged in different directions, X, Y, Z directions. Then we can identify what is needed to be done. So, for instance, reducing the sled's response to vibrations and external loads, in what direction, that can lead us to, okay, we need to do some rotational mitigations. So we put in supports that are erasing those motions of risk. And we want to raise our resonance frequencies upwards to get them higher, to get them stiffer, to get them more sound. Yeah. This is from when we test our moving, this is for moving the sleds, and we are designing then all our equipment accordingly to avoid the frequencies of risk. Same we do with the ships. Now we're mounting these big steel frames around the ships. Building it up, putting vibration isolation, ending up with some dust protection. Now we are looking into, this is from the test this week, where we are looking at the transportation into the new museum. And this is so far for future, with our goal to get this a safe journey and establish the new museum. This is also under now construction last Friday. And that was it. I'm very sorry I didn't practice on this before I came here with time.
I feel like a terrible villain for stopping you, but I want to be sure we've got time for questions because it's fascinating. So can we throw it out? Questions from the audience? Please, here.
Thank you very much for your presentation. I think that the problem of archaeological wood and the management of archaeological wood, it is one of the most interesting teaching in conservation science. And we see what could be the effect of treatment on the wood that is a living material. And sometimes you need years before that effect produce a measurable effect. And the PhD treatments and all the other treatments has shown they affect sometimes in a time span of 40 years. So it's a very important teaching, in my opinion, for all of us. Treat wood is always dangerous because we can understand what's happened in a long time. But my question was about the creep. Because many similar cases around Europe has always the same problem. That is the problem that came from the structure of the support. The design of these ships were made for working against the pressure of the water. Okay, so basically they work in compression. When they stay inside the museum, in all cases, you have a support system that is made by some points. And the structure of the ship, it doesn't work as it was designed for, because she moves in this way. So, because, for instance, even with the Vasa, they have the same problem. I'm not sure that is creep. It could be possible to be plastic deformation due to deformation of the ships, of the structure. And we have similar cases in a more recent ship in the National Museum in Milano that have exactly the same problem.
Yeah. I don't know what the actual I just agree with you. I didn't catch the question of it, but ships are really difficult. And even if this had been a new ship built when we exhibited this particular ship in 1932, in the same way, a new ship, fresh wood, it would suffer from deformations, of course. And archaeological wood just adds to that complexity enormously, because also the mechanical joints, friction between boards, everything is sort of making this highly complex. And I have actually been employing some of the methods I've been using on our ships and developing there on the Vasa ship as well. And they have also big problems and a very heavy structure that is peg impregnated and actually collapsing on itself.
Thanks for the presentation. I have a couple of questions based on the vibrational behavior of the ship. You said that you used isolators to diminish the forces. What is the logic to choose isolation instead of dissipation? It's a curiosity.
Sorry, isolation instead of?
Dissipation, dissipators.
Dissipators.
Let's say if you use a system of isolation, you augment the period and you decrease the forces. If you use dissipation, you lower there are two methods to deal with vibration, and I wanted to know if you choose them for a reason, let's say.
Okay, what I can say about we use vibration for the structural analysis to see what vibrations are harming the ships the most. The mode shapes, they are expressions of harming deformations in the ship, and they occur at different frequencies. And what we found out, we want what I went through very fast is that we put our objects in very stiff structures. Very, very stiff structures above 20 hertz. That's why we have these enormous steel structures. So they are very stiff. That means that what we then want to do is to everything that goes from the stiff frames over to the ships will be of a higher frequencies than the vulnerable frequencies to the ship. And then we want to dampen from the building site the low frequencies. We take them away with these air springs. Okay. So we take away things that goes down to 0.5 hertz.
Yes, makes perfectly sense.
Yeah.
Another question, very slow, very easy, is how did you manage to address local modes? I mean, in a structure big like that with this complexity, I expect some global modes of vibration and more local modes. I think that this system deal with global modes. With local modes, you did have anything, or they were not taking so much mass?
Yeah, we have done that as well, but I'm terrible with time and to focus on I wanted to sort of show you the big picture of what we're doing. We're doing load distribution, deformation monitoring, and vibration mitigations with the structural analysis through ODS. And the modes, we put a load of sensors on our objects. And then if we find areas of special interest where we see that something is going on, maybe around cracks or where the structure is especially vulnerable, then we put lots of sensors around that area on each side of a crack, for instance, we can put 4 sensors around the crack, and then we look at the transformation between the sensors. So yes, but what I showed you is just the global, but we also go into local mode shapes.
We've got time for one very quick question. Well, we don't really, but we could do. I'm going to ask a very quick question. I'm going to steal it. The fact that you had 3 ships that are obviously all very different to one another, but the fact that you had essentially 3 data points, did you learn anything from across all 3 ships that you wouldn't necessarily have been able to confirm in isolation? Were there any of those kind of cross correlations that you found in the behavior, or are they just so distinct and so different that you weren't able to kind of pull anything apart from that?
Yeah, what we learned was that they are very different, and the assumption that the museum has had for many, many years now is that since you have so many fractures throughout the ships, and they're put together from many, many pieces of wood, and that the preservation state is quite poor, the assumption has been that it doesn't hang very well together. So they've sort of thought that climate fluctuation wouldn't affect the global structure as much as it has turned out. And that has also been very different from between the ships.
Fantastic. Okay, thanks so much. Another round of applause, please.